timekeeping and are still widely seen in homes, parks and other public spaces. Sundials measure solar time, the time reckoned by the position of the sun in the sky. But interestingly, they aren't particularly good timekeepers. Averaged over an entire year, the time shown by a sundial will be correct, assuming of course it has been set up correctly for the time zone and longitude. But on a given date, it can be up to 15 minutes fast or 15 minutes slow on the time you use for day-to-day activities. The graph shows for Greenwich the difference between solar time and GMT. This variation runs between the sundial being 14 minutes and 15 seconds slow on February the 12th, so when it shows a time of 12 noon, it will be 12:14 and 15 seconds GMT. The sundial being 16 minutes 25 seconds fast on November the 3rd, so when it shows a time of 12 noon, it will be 11:43 and 35 seconds GMT. In this video, I'm going to talk about the equation of time. That's the difference between the solar time measured by a sundial and the mean solar time. At any location on zero longitude line, the mean solar time is simply Greenwich Mean Time, GMT. At other places, the mean solar time will depend on your longitude. As I'll explain next, the reason for the equation of time is the length of a solar day isn't always 24 hours, but varies throughout the course of the year. It's at its shortest in mid-September and its longest just before Christmas Day. If we look at this graph, the y-axis shows the difference in seconds between the length of the solar day and 24 hours. So for example, 10 means 24 hours, 10 seconds. 20, 24 hours, 20 seconds. Minus 10, 23 hours, 59 minutes, 50 seconds. The variation in the length of the solar day isn't due to the change in the Earth's rotation speed. Although it does vary a little, the effects are both small and unpredictable, whereas the variation in the length of the solar day is large and predictable. There are actually two different causes of this variation. Firstly, the Earth moves in an elliptical orbit around the Sun, and secondly, the Earth is tilted on its axis. I'll now talk about each of these effects in turn. The Earth takes 23 hours and 56 minutes to make a complete rotation on its axis. However, a solar day is on average 24 hours long. This is because during the time it has performed one rotation, the Earth has moved around the Sun a little in its orbit. For example, if we take the point in time where the Sun is at its highest in the sky, marked with a purple dot, then one rotation later, because the Earth has moved along in its orbit, the Sun isn't overhead at this point. It takes an extra 4 minutes for the Earth to rotate a little further to reach the point where the Sun is once more at its highest in the sky. And that's why a day is on average 24 hours. Because the Earth's orbit is elliptical, its distance from the Sun varies during the year. It is at its closest in early January, furthest away in early July. When the Earth is closest to the Sun, it moves more rapidly in its orbit, and when it's furthest away, it moves more slowly. In January, when the Earth is moving at its fastest in its orbit, it takes slightly more than one rotation plus 4 minutes for the Sun to be at its highest point in the sky on the following day. So this means that the solar day is slightly longer than 24 hours. In early July, when the Earth is moving at its slowest in its orbit, it takes slightly less time than one rotation plus 4 minutes for the Sun to be at the highest point in the sky on the following day. So this means that the solar day is slightly shorter than 24 hours. The graph here shows the variation in the length of the solar day if the eccentricity of the Earth's orbit were the only factor. The second factor which affects the length of the solar day is the tilt of the Earth's axis. Many, if not most people, know it's this tilt which causes the seasons, but at first sight it isn't immediately clear why the tilt should also cause the length of the solar day to vary, and many people struggle to visualize this. So I'll talk about this next, and I hope that my explanation is easy to follow. Astronomers use a system called celestial coordinates, where all the celestial objects, including the Sun, the planets and the stars, are given a position on an imaginary sphere known as the celestial sphere surrounding the Earth. The latitude is known as the declination and the longitude is the right ascension. The Sun moves in the path shown on the celestial sphere. The line of zero right ascension, shown as the green line, is the Sun's position at the March equinox. What you can see from the diagram is at the equinoxes in March and September, the Sun is moving quite steeply in declination, and because of this, its daily change in right ascension is slightly smaller than at other times of year. At the solstices, in June and December, the Sun's declination doesn't change very much at all. It remains at a declination of 23.4 north or south for the few days around the solstice. Its change in right ascension is slightly larger than at other times of year. Take a look at the picture in 2 dimensions from a point directly above the North Pole. Then the Sun's apparent orbit isn't circular at all, but it's flattened because of its tilt. If you watch the Sun as it goes round this apparent orbit, the right ascension of the Sun changes faster at the solstices and more slowly at the equinoxes. Astronomers actually measure right ascension in hours, and there are 24 hours in a circle. So 1 hour of right ascension is equal to 15 degrees, but I've decided to stick with degrees for this video. Around the time of the solstices in June and December, when the right ascension of the Sun is changing fastest in its apparent orbit, it takes slightly more than 1 rotation plus 4 minutes for the Sun to be at the highest point in the sky on the following day. So this means the solar day is slightly longer than 24 hours. Around the time of the equinoxes in March and September, when the right ascension of the Sun is changing slowly in its apparent orbit, it takes slightly less than 1 rotation plus 4 minutes for the Sun to be at the highest point in the sky on the following day. So this means the solar day is slightly shorter than 24 hours. This graph shows the variation in the length of the solar day if the Earth's axial tilt were the only factor. As you can see, it will be longest at the June and December solstices at around 24 hours 20 seconds and shortest 23 hours 59 minutes 40 seconds at the 2 equinoxes. The combination of the 2 effects is shown as the black line in the graph below. As I mentioned near the start of the talk, the longest solar day is around 23rd of December and the shortest around the 17th of September, although these dates vary a little from year to year. The other interesting thing it shows that although a day is often thought as being 24 hours long, there are actually only 4 days a year when the natural day measured by the motion of the Sun in the sky is 24 hours. And even then it is not exactly equal to 24 hours to the nearest millisecond. So putting it all together, firstly to recap, the equation of time, which is shown on the graph and we've met earlier, is the difference between solar time, or the natural time shown by a sundial, and mean solar time, time assuming all days are 24 hours long. and it's caused by variation in the length of the solar day throughout the year. So, if we start in region A solar day is longer than 24 hours. So that means the middle of the day, where the sun is at its highest in the sky, will get progressively later and later each day. So a sundial will progressively lag behind the mean solar time. This continues until February the 12th, when a sundial will be 14 minutes 15 seconds slow. Now in region B, our solar day is now shorter than 24 hours. So that means the middle of the day, where the sun is its highest in the sky, will get progressively earlier each day. This continues until May the 15th, when the sundial will now be 4 minutes fast. We move across to region C. A solar day is once again longer than 24 hours. So this means the middle of the day, when the sun is at its highest in the sky, will once again get later and later each day. This continues until July the 26th, when a sundial is 6.5 minutes slow. And finally, in region D, a solar day is once again shorter than 24 hours. So the middle of the day shifts earlier, and this continues until November the 3rd, when a sundial will be 16.5 minutes fast.